In some cases, it might be difficult to even simulate the distribution f. However, sometimes it is possible to write f in terms of a more easy to simulate distribution in a probabilistic way. If this is the case, then we can exploit this relationship to simulate f through this other distribution g. Some well-known relationships between distributions are the following. For a random variable u, which is uniformly distributed, if we sum the logarithms of u, we sum them up to nu and we multiply with -2, then this new random variable follows a chi-squared distribution with parameter 2 nu. If we do the same, but we take a sum to a and we multiply with minus beta, then we have a gamma distribution with parameters a and beta. And then finally, if we divide a sum of logarithms by another sum, a larger sum of logarithms, this will give us a beta distribution. Transformation method algorithms will exploit these relationships for simulation purposes. So if we can simulate a uniform distribution, we can also simulate, for example, a beta or a gamma distribution. Using two uniformly distributed random variables, u1 and u2, we can generate a standard normal distribution through the Box-Muller transform. So based on u1 and u2, we will make a pair of random variables, x1 and x2. x1 is -2 logarithm of u1 times the cosine of 2 pi u2, while x2 is the same factor, but you multiply with the sine of 2 pi u2. In that case, x1 and x2 together will be IID and they will generate random numbers from a standard normal distribution. The reasoning behind this relies on polar coordinates. So assume that r and theta are the polar coordinates of x1, x2. Furthermore, we know that if x1 and x2 are each of them standard normal distributed, then the couple x1, x2 will be a bivariate standard normal distribution. And for a bivariate standard normal distribution, we know that x1 squared plus x2 squared will be equal to r squared. And this will follow a chi-squared distribution with 2 degrees of freedom. Furthermore, a chi-squared distribution with 2 degrees of freedom is the same as an exponential distribution with lambda equal to 1/2. And in the previous part, we saw that we can simulate this by using minus the logarithm of a uniform distribution divided by its parameter. Furthermore, since the Gaussian distribution is rotation invariant, the angle theta will be uniformly distributed over the interval 0 to pi. So the random variable theta can then be simulated using a uniform distribution on 0, 1 times 2 pi. We then use polar coordinates. So polar coordinates tell us that x1 is r times cosine of theta and x2 is r times sine of theta. And then we replace r and theta with the simulated values. So the couple x1, x2 that we generate this way follows a bivariate standard normal distribution. And then we know that in this case x1 and x2 each follow a standard normal distribution, a univariate standard normal distribution. This algorithm to simulate a standard normal distribution is called the Box-Muller algorithm. This algorithm to create a standard normal distribution is an exact algorithm, as opposed to the approximate algorithm that we saw in the first part, and furthermore it is faster than the algorithm than the previous proposition as well. We already saw how to simulate an exponential distribution. A Poisson distribution, on the other hand, is not as easy to simulate, but it is possible to obtain Poisson distributed values using the exponential distribution. For n, a discrete variable following a Poisson distribution with parameter lambda, and x1, x2, x3 and so on are all exponentially distributed with the same parameter lambda, then it is possible to prove that the probability that n is equal to k, so the probability that my Poisson variable has an outcome k, this probability is the same as the probability that a sum of k exponentially distributed random variables is smaller than 1, but the sum of k plus 1 of those variables is larger than 1. So in practice you will start by simulating a random variable which follows an exponential distribution. You look at its value. If it is smaller than 1, you continue, you do the same, you add another random variable which is exponentially distributed. These are simulated, or these can be simulated using inverse transform sampling. You add x1 with x2. If it is still smaller than 1, then you will create a new variable, x3, exponentially distributed. You add that one to the sum. You see if it's larger than 1 or smaller than 1, and so on. And so you continue this process until you depass 1. Let's say that after adding x5, the sum becomes larger than 1. So x1 plus x2 plus x3 plus x4 plus x5 is larger than 1. So we know that we depassed it. According to formula 5, k plus 1 is then equal to 5, and k will be equal to 4. So we say in this case that the simulated outcome for n is equal to 4. If we then pour this into an algorithm, we obtain the following code. Again, we start by defining the sample size, n. Sims is null will create an empty variable in which we will store our outcomes, our simulated values. And we set the lambda equal to 2. And then we start generating n Poisson distributed values. We start by initializing the counters at 0. T0 is the sum of the exponentially distributed variables, and k will be the counter to indicate how many terms our sum will contain. Then, as long as the sum is smaller than 1, we will generate a new exponential distributed value. We generate this using the inverse transform sampling method, so minus log of a uniform distribution divided by lambda, and we add it to the previous sum. So we update t by adding another exponential variable, and we also update our counter, so k will become k plus 1. Then, once we go out of this loop, so once we have a sum which is larger than 1, we add the value for our Poisson distribution, and this value will be k minus 1. K minus 1, why? Because our latest k is the one that got us out of the loop, so it's the k for which that the sum was larger than 1. So we have to subtract 1 and use k minus 1 as the value for the Poisson distributed random variable. So this gives us a series of values, and on the right you see the histogram for the simulations, which looks indeed like a Poisson distribution with lambda equal to 2. An alternative method for generating a Poisson random variable is given by Knud's algorithm. This algorithm is basically the same as the previous, but we have rewritten the equation, or we have rewritten the comparison. In the previous algorithm, we compared a sum of exponentially distributed random variables with the value 1. And these exponentially distributed random variables were generated using a negative logarithm of a uniform distribution over lambda. This is the same as comparing the sum of the logarithms with minus lambda. Or, if we take an exponential of this, it will become the product of uniform distributions with e to the power minus lambda. And so that is what Knud's algorithm does. It makes a product of uniformly distributed random variables and compares it to e to the power minus lambda. These two algorithms are quite simple, but they are only practical for smaller values of lambda, since on average you will require to generate lambda times an exponential.